We're starting a new chapter today, chapter 6, and we're going to be talking actually the next couple of days about graphing exponential functions. And I've decided to break this up into two parts. So even though my objectives say that we're going to graph exponential growth and exponential decay, actually today we're going to focus just on exponential growth, and then tomorrow we'll look at the exponential decay function. So right off the bat, let me show you what is considered to be the parent exponential growth function. And we describe it this way. This is a function where we have this number sitting below the exponent. We would call that the base of the exponent. And to make exponential growth, this number that we call b has to be greater than 1. Tomorrow, we will look at b as being between 0 and 1. Same function, it looks exactly like this, but when we change this number that we call b, then if it's between 0 and 1, then it becomes exponential decay. But today this number should be greater than 1, so we're going to be looking at the graph of exponential growth. Alright, we're going to actually sketch a sample here, but this is going to be, as far as the type of graph, it's going to be a continuous, meaning there are no breaks. It'll flow left to right continuously without any hesitation or break in the line. It'll be one-to-one. Remember what a one-to-one function is. And then we could also describe it as increasing. Okay, there's three ways really of describing this graph. So you'll understand more where we get this term increasing when we do a little sketch here. So let's just go ahead and do a sample. I'm going to sketch the graph of the function f of x equals 2. We're going to make b become 2 raised to the x power. So notice it is going to be growth because my b number is greater than 1. Alright, so what I want you to do on your homework when you're given these functions, and this would be an example of a parent function, when you're given these functions, then we're going to make a table. I want you to show me the table. And you can use the same 5 domain, that's another word for input. You can use these same 5 numbers for every function. Just remember that now when you're inputting a number in for x, you're actually inputting into this exponent. So for example, if I let x be 0, 0 is my input, f of 0 means 2 to the 0 power, which is 1. So I know that the point 0, 1 is on the graph. And that's going to be true for every parent, a function that's not translated where there's no number besides 1 here in the front. It's always going to be true that the y-intercept for the parent exponential growth is going to be 1. Alright, let's try another input like 1. 2 to the first power is 2. Let's do input 2. 2 to the second power is 4. So let me go ahead and plot these. We got the point 1, 2 on the graph. We have the point 2, 4 on the graph. So you can kind of get an idea as we travel to the right, as we choose larger values for x as inputs, the graph is going to continue to go up. In fact, it's going to go up quite sharply. For example, if we input 3, then we've got 3, 8. 4, 16, 5, 32. You can see how we're just getting larger and larger values for y just by increasing x by one number. If we let x be 6, just go up to the next number, we get 32, or I'm sorry, 64. 2 to the 6th power is 64. So classic exponential growth, as we choose larger numbers for x, just increase one at a time, we can see how y really starts to take off exponentially. That's where we get the term. Alright, so now always choose the opposites of these so you can get an idea of what happens going to negative infinity. So remember what negative exponents do. 2 to the negative 1 is the same thing as 1/2. Negative exponents cause you to flip the base, and then you can change the exponent to positive. So for input -1, we have 1/2. Input -2, we get 1/4. 2 to the -2 is the same thing as 1/2 squared, which is 1/4. That's just going to be a little closer to the x-axis. Okay, so we got our 5 points. Those are going to be the same 5 inputs that you use. Obviously the outputs will change from problem to problem. But I want you to pay attention to a couple of things as we, first of all, we'll go ahead and sketch this graph as best we can. All right, so now do you see why we say that the function is increasing? That means as we travel from left to right, it's just going to continue to get larger, go further up the y-axis. Okay, so let's state the domain. Remember, domain means the x values that would be included in this particular graph. Well, it goes forever left according to this arrow, and it goes forever right according to this arrow. It's going right and up. So the domain will be all real numbers, but instead of saying all ARN like we've been doing in the past, I want you to get used to looking at a couple of different notations. And this first one is called interval notation. And interval notation is, we describe the left side. Notice I've got parentheses. We describe what happens going to the left. It's going to -infinity. And then we describe what happens going to the right. That's going to +infinity. So that would be another way of saying all real numbers, but we're using interval notation. Let's do it using something we're more familiar with, using inequalities. All x such that we could say that x is between, here's a between statement, x is between -infinity and +infinity. So that's two ways of saying the same thing, the all real numbers, but I want you to choose one or the other and use that going forward for all real numbers. Okay, so let's take a look at the range. Range means what y values are involved if we look up and down. Well, it doesn't go beyond or below the x-axis, obviously. It looks like it's getting really, really close, and we're going to talk about that more in just a minute. It's getting really close as we choose smaller values, more negative values for x. We just keep getting closer and closer to the x-axis, but the interesting thing is we will never touch it. We'll never get there. If we let x be -2 million, that's just going to be a really, really small fraction, but it's still going to be greater than 0. So we're never going to have a situation where y, or this function, is equal to 0. There's no way to input a number for x to cause this function to equal 0. So we show that graphically by making this graph get really, really, really close, but it will never get there. So for the range, since we're never getting all the way down to where y is 0, using interval notation, we could say that the range is from 0 at the bottom to +infinity. All right, and let me just, while I'm here on interval notation, this parentheses says that 0 is not included as part of the range, and we already said that that's because the graph is never going to get to the x-axis where y is 0. If 0 is included, just want to show you a what if 0 was included in the range, then my interval notation would look like this. I would use this square bracket, and I never use a square bracket for infinity because we can never put a bound on infinity. It never stops. But if a number is included, this would be the example of saying y is greater than or equal to 0. All right, by saying this square bracket, we're saying that 0 is part of the range. When we leave it as a parenthesis, then it's like saying just greater than 0. So that's just another word about interval notation. I just want to make sure you get familiar with that, because that's going to be important not only in this class but in future classes. Okay, so we've identified the domain, we've identified the range. Now let's talk about this word called asymptote. What is an asymptote? There's a vertical and a horizontal usually. In this case, we just have a horizontal asymptote. And let me first of all give you the definition. An asymptote is a line. First of all, I want you to understand that it is a line that a graph will approach. In other words, we're going to get closer and closer to it, but we're not going to touch it. A line that a graph will approach but not touch. Well, you can see that that's what's happening here with the x-axis. We're approaching it forever as x approaches negative infinity, but we're never going to get there, and we talked about that earlier, and it's because we cannot choose a number for x that would cause this to be 0. So the horizontal asymptote for this parent function, f of x equals 2 to the x, will be the line y equals 0. And that's just another way of saying the x-axis. On the x-axis, every y coordinate is 0. And remember that if you're writing the equation for a horizontal line, it should always say y equals. Okay, x equals lines always run vertically. Okay, so there is a horizontal asymptote, a line that our graph is approaching but will never touch, and that is the line y equals 0. Okay, so we've looked at what exponential growth looks like. So let's do some more examples like your homework will ask you to do. So again, make sure that you show me the table, and you can use those same 5 inputs. That makes it pretty easy. If I input 0 for x, 4 to the 0 is 1. If I input 1 for x, 4 to the first is 4. 2 for x, I get 16. Negative 1 for x, I get 1/4. Notice it's just the reciprocal of the output when I did input 1. And then negative 2 will be the reciprocal here, because 4 to the negative 2 is 1/16. So a good thing about the table is that it identifies the biggest value for y that I'm going to have to plot. And I do want you to plot all 5 of these points on your graph. So that's going to require that you make some changes to the units. Obviously, I cannot get up to 16 with this graph section. 5, 6, 7, 8. I think I've got 10, maybe 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. I can only go up to 9. So I'm going to make the y-axis only in 2s. It will not be necessary to change the x-axis, but I am going to need to change the y. So make sure that you change your units to make your table of values fit. Alright, so here's my y-intercept of 1. So I'm going to put that right there. And then 1, 4 would be here. Remember, I'm in 2s. 2, 16. 2, 4, 6, 8, 10, 12, 14, 16. And then going this way, it's really just getting closer and closer to the x-axis. These are just fractions, and obviously you're just guesstimating, but as you move left, you should be a little closer than the one to its immediate right. All right, so let's do our best to connect these. And classic exponential growth goes up the y-axis as we choose bigger numbers for x. And if that were a homework problem, we would almost be done. We just now need to state the domain and range. The domain for all of these is going to be all real numbers. So once again, you can use interval notation to describe the left side and the right side. Or if you wanted to use, as we've done in the past, the inequality notation like I did here. That would be fine. Just we're going to stay away from ARN. Okay, so the range, once again, it's going to be all of the y's that are above 0, not including 0. So we will say from 0 on the bottom and then going up to positive infinity heading upward. Or once again, you could use inequalities. I didn't show it there, but you could use the inequality such as f of x, such as f of x is greater than 0, okay, not including 0. So either one of these would be okay to state the range. And that would be your answer to this homework problem. Okay, so now that we understand what the parent looks like, let's review transformations of parent functions. So we've already been doing this for other parents, like this parent function. We said that here's how we transform it or translate it. And we said that this value h indicates a horizontal movement. If h is positive, then we move to the right. If h is negative, which is going to cause this to become plus, we move to the left. K tells me about vertical movement. Plus means up, minus means down. And if I did have a number in front, that's going to indicate either stretch vertically or compression vertically. Well, that's exactly the same thing that's going to happen with this transformation. A is going to indicate vertical stretch or compression. H is going to indicate whether or not I move horizontally and right or left. K is going to indicate vertical move up or down. K plus means up, minus means down. All right, so we should be used to this by now. Let's go ahead and sketch the graph of this. And the way I want you to do these is I want you to treat these as transformations of the parent. So I'm going to lift out the parent function from this. I know it's got a lot of stuff around it, but the basic parent function included is this one, y equals 2 to the x. Well, we've already done that table. We did that with our very first example, but I'm just going to write the numbers here again. If x is 0, y is 1, 1, 2, 2, 4, negative 1, 1/2, negative 2, 1/4. Okay, now here's what I want you to show in your work. Start with the parent, and then we're going to do a progression of the transformation. How does the transformation affect this parent function? And or you could actually draw the parent like this. Go ahead and put these parent points on here. 0, 1, 1, 2, 2, 4, negative 1, 1/2, negative 2, 1/4. Okay, so I'm not going to actually draw the line, but I'm just going to use those like we've done in the past as reference points. And now I'm going to do the shift. If you want to show me tables, I think I showed an example of this in class. Some people like to do tables. This plus 3 indicates left 3, and this minus 5 indicates down 5. So we could do a table and plot from the table. Okay, left 3 is the same thing as subtracting 3 from each of these x's. Alright, so let's just take one at a time. 0 minus 3 is negative 3, 1 minus 3 is negative 2, 2 minus 3 negative 1, negative 1 minus 3 negative 4, negative 2 minus 3 is negative 5. And then to accomplish the down 5 movement, it's like taking each of these y's and subtracting 5 one at a time. 1 minus 5 is negative 4, 2 minus 5 is negative 3, 4 minus 5 negative 1, 1/2 minus 5 is negative 4.5, 1/4 minus 5 is negative 4, and 3/4. And so I could plot this blue table, and that would represent my answer. You could also, if you feel comfortable, you could just plot these points. This is the parent, and then count. We've done this in the past when we dealt with absolute value, square root, cube root. So let's just start up here. This is my point from the parent the point 2, 4. Okay, so each one of these red dots, I'm going to move left 3 and down 5. And the blue is going to represent my answer. And so I think I'll just erase these red ones as I'm done. We've done this in the past. Okay, so here's 1, 2 from the parent, and then let's go left 3 and down 5. 1, 2, I went left 3, down 5. All right, done with that one. Let's take the next one. Here's 0, 1. So I'm going to go left 3, down 5. All right, that's done. Okay, same thing here. This is negative 1, 1/2. So I'm going to go left 3, down 5. Make sure you maintain that half. And finally, left 3, down 5. All right, so you can see once you learn those translation rules, it makes it easy to transform any parent. Once you understand what the parents look like, the transformation should begin to get a lot easier. Now, a couple of things we need to notice. We no longer have a horizontal asymptote here at the x-axis, okay, because our graph has shifted. It shifted 5 units down. So the effect of that is to shift our horizontal asymptote 5 units down. The entire graph, in essence, shifted 5 units down, which affects our horizontal asymptote. So now I'm approaching the line y equals negative 5, but I'm never going to touch it. Okay. And so that would be the graph. This is y equals 2 to the x translated 3 places to the left and 5 down. And now let's do the domain and range. The domain's still going to be all real numbers. The range is going to change a little bit since we've shifted our graph downward. The lower part will be negative 5. And we're not including negative 5 because we're not actually ever going to touch that line with our graph. And then we're going to go upward forever, positive infinity. And again, you can use inequality notation if you choose. Okay, so that is your answer for Roman numeral 2a. Now let's try Roman numeral 2b. This time, if you notice, going back to this problem, I meant to mention this, but the A number, the number that indicated vertical stretch or compression, well, the A number here is understood to be 1. So in essence, we did not have vertical stretch or compression. When A is just 1, that does not stretch or compress. Well, that's not going to be the case here. A, in this case, is 0.1. B is 6, and we do not have a horizontal shift. Notice there's nothing being added or subtracted to x, but we are going to have a vertical shift. All right, so I think I'm just going to show this one using tables. So make sure you just show me your parent function first. This is going to be the parent y equals 6 to the x power. Okay, notice I just pulled that out. F of x equals b to the x is the parent. So let's do a table for that first. 0, 1, 1, 6, 2, 36, 6 to the second. And then do the opposites. Negative 1, 1 sixth, negative 2, 1 36. And you might want to just go ahead and plot those. So not saying you have to, but I notice before I get too busy into this, I notice that I've got to try to plot 36 on here, and I only have 9 places, so we could do this in 4s. That would make them all fit. So I'm going to guesstimate 0, 1, about right there. 1, 6, 2, 36, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then these are just going to be really, really close. All right, I'm not going to draw the actual line, but I'm just going to use these as reference points, and then I do want you to show me the table. Okay, so let's change color, and let's do this is a dilation, multiplying this graph. This is going to be vertical compression. And remember when we've run into this in the past, what we're actually multiplying by here is just the y of the parent, just the y coordinate. So I'm going to grab a calculator. You probably want one for this one. And I'm going to show multiplying in this table. I'm just going to take it a step at a time. I'm going to show multiplying by 0.1. Now notice the x's are not changing. The effect of multiplying here does not do anything to the x's, but it will affect the y's. Alright, so if you have to, you can grab your calculator and multiply each one of these y's separately times 0.1. 6 times 0.1, 36 times 0.1, 1/6 times 0.1. I'll give you the rounded decimal. That's just 0.017. And 1/36 times 0.1. 0.0028. Okay, so we've taken care of the vertical compression. We do not have anything to do to the x coordinates as far as a shift left or right because h is 0, but we do need to show this shift of 3 units down. And so once again, I'm just going to take this one step at a time, and I'm going to call this down 3, and nothing has affected x. I'll just write those down. But for each one of these y's, I'm going to subtract 3. Down 3 is another way of saying subtract 3. Alright, so once again, you can grab your calculator. 0.1 minus 3, negative 2.9, 0.6 minus 3, negative 2.4, 3.6 minus 3, 0.6, 0.017 minus 3, negative 2.983, and then 0.0028 minus 3, negative 2.9972. Alright, so let's plot these, or if you want to just take each of these and do your best to shift them down 3, but then it makes it tough to multiply the y by 0.1. So I think in this case it's just easier to plot these 5 points that we have in this table, and once those points are plotted, that will be the graph of our answer. Alright, so 0, almost negative 3. Real close. Oh, I forgot I'm in 4s. Well, now that I've done the dilation, of course, I don't need the 4s, so I guess we can change that. It's not going to be necessary. You don't have to graph the parent, but for some people, they like to look at the parent. Since I can put all of these easily without changing my units, then I'm just going to make them go back to 1s. Alright, so 0, almost negative 3, 1, about negative 2.5, 2, and a little bit more than a half, negative 1, and real close to negative 3, and negative 2, even closer to negative 3. So you can see this K value always tells us what our new horizontal asymptote should become. And so again, this is going to be a rough sketch. The big thing is I need to be able to look at your table to know exactly what points you are connecting here. It's not real good, so let me try that again. All right, going both ways. You should not draw below y equals -3. That's our new horizontal asymptote. So if you draw a line that goes like this forever, then it's wrong. It will not touch y equals -3. Okay, and then domain, once again, is all real numbers. Range, this time, it's going to be from -3 going upward to positive infinity. Okay, so that's an example of a transformation of a parent function. And then finally, you have a word problem, number 19. I thought I would do this one because it's very similar. It looks a lot like it. So let's just talk our way through. This is perfect example of real-life exponential growth. A virus spreads through a network of computers. Every minute, 25% more computers are infected. If the virus began at only one computer, graph the function for the first hour. So first of all, let's write that function in function notation. Okay, remember y equals a times b to the x. It's not really going to be a transformation, so I won't have to do the minus h plus k. But this is typical, if you will, the format for exponential growth or decay, but we know it's going to be growth because it's growing. The number of computers that are affected are growing by 25% each minute. So B, another way of looking at B is it is called our growth factor. And here's how you find the growth factor. Here's how, and when you do number 19, you'll do the same thing. If you want to know what B is, always start with 1 and then add whatever the percent is in decimal form that you're told the growth is happening at. It's happening at 25% per minute. Okay, so let's do 1 plus, and I'm just going to write down the decimal form of 25%. Well, 1 plus 0.25 is 1.25. Okay, so my B number is 1.25, and that's another way of saying the growth factor. And again, if you want to find it in these word problems, you always start with 1, and for growth, you always add, and you'll always be given a percentage of growth, and so just change that percent to decimal, and you'll have it. This A number in these word problems, I know it refers to when we're graphing, it tells us about stretch or compression. But in these word problems, it's like the initial value. Like, where did you start? And this virus began at only one computer, so we don't have to write 1 times, but I'll go ahead and do it. A in this case would be considered 1. Okay, so our function that we're going to be graphing is f of x equals 1, which you don't really need, times 1.25 to the x power. Okay, so we have our function, and so let's make our table. Now this time, unlike the graphing problems that we did where it's just purely graphing, this time our domain, or that's another way of saying the inputs, need to be something different, something that relates to what we're talking about in this problem. We notice that the virus is affecting computers at a rate of 25% per minute. and we want to know the first hour of the spread of the virus. Okay, so that's going to impact what we choose for X. Okay, so before we start graphing, obviously we need to build a table. We can do anything we want. We're going to go up to 60 minutes. We don't need to go any further than 60 minutes. We can start at 0. All right, and we're told that it began at one computer. So after 0 minutes, one computer is affected or infected, and we already knew that. So that table just reinforces what the problem told us. We could do these increments, maybe 15s, or since we have, let's see, 1, 2, we have 9. We can do 10 minutes at a time. Let's just do that. X is going to refer to the number of minutes. That's the input. So anytime we do a graph of a word problem, we should always label the axes. This is going to be minutes, and the Y will represent computers infected. Okay, so let's see. Let's let X be 10. Grab our calculator, and when we do 1.25 raised to the 10th power, we get 9. We'll just round 2 decimal places. 9.31. 20 minutes. Okay, do the same thing. 1.25 raised to the 20th. 86.74. 30 minutes. X is 30, so 1.25 raised to the 30th. 807.79. 40 minutes. Wow, it's going pretty fast, isn't it? 1.25 raised to the 40th. 7,523.16. And these are computers, so we probably should just round, but that's okay. 50 minutes. 1.25 raised to the 50th. We'll just go ahead and say 70,065. 70065, and then finally 60 minutes. So the first 60 minutes, or first hour, it is important that you understand why X represents minutes, because that's the unit of time at which the infection is taking place, 25% per minute. So let's let 1.25 be raised to the 60th power, and we get a pretty big number. 652,530. Wow, a lot of computers in just 1 hour at that rate, increasing at 25% per minute. After 1 hour, that many computers have been infected. So let's try to plot these. Obviously, we're going to have to change our units. We can make these in, let's see, 100,000. That's more than enough. And I'm going to do our units in tens. Okay. So obviously 0, 1. I mean, that's just really, really close to the x-axis. So is this. Maybe just up a smidgen. 20 up just a little bit more. We're not going to really see any big significant jump until we get obviously to these bigger numbers. So 10 minutes, 20 minutes, 30 minutes, it should be a little bit higher. 40 minutes, we're at 7,000. It's probably still a bit too high. So these are really, really close. Don't get too bogged down. These are really, really close. Until we get to 70,000, and that's a little bit, let's see, 10, 20, 30, 40, 50. So we can move that up just a little bit. and then 60, we're up at 1, 2, 3, 4, 5, 600. It's in between 6 and 700,000. So we have a graph that hugs the x-axis pretty close, and then you can see it jumps pretty quickly once we get up to 50 and 60 minutes. Alright, and I would actually be okay, since it said strictly for the first hour, there really isn't a need to extend this forever and ever. I would just let it stop there. So it would look something like that. So that is your answer for, this is not one that you have to do, but I would use this as a model when you're doing your number 19. Set up the function just like we did. It's going to be you get the growth factor just like we did. If they tell you that the beginning number of whatever is, well, whatever it is, whatever they start with, that number will be placed in A's spot. And then X for these word problems represents typically a unit of time. So read your problem and see if the growth is happening each hour, each day, each month, whatever it is. That will be your input for X, and so you'll need to label your x-axis accordingly. Okay, so that is exponential growth 6-1 part 1, and let me know if you have any questions.